Hello physicists. So the first video in this Chapter 8 series is meant to review some of the work we did on springs in our class on Wednesday. In this problem that I have set up here, it's a bungee jumper problem. So you have a jump point. Look at the diagram on the left first, please. And there's a jump point that's that we set up, and then 9 meters below that we're setting up the 0 point. That's because the cord is 9 meters long, the bungee cord. So at 9 meters from the jump point is when the cord actually starts to act like a spring. Before that point, it's just free fall. Some distance below that, the cord's going to stretch from this point 0 to this point we're calling the turning point. The cord is going to stretch. First, it's going to slow down, and at the turning point, they're going to start making their way back up. What we're asked to do is, assuming no friction and all that kind of stuff, just using springs and gravitational energy. How far are they going to fall? Where is this turning point? All right, so I set up a sketch here of the potential energy. Now, in the diagram to the left, distance is measured vertically because it's a jump, but we're still calling it x. X is positive. Above the 0 point, x is negative below the 0 point. What we've done in this diagram, the potential energy diagram, is we've turned that 90 degrees. So x is positive to the right, x is negative to the left, and we're dealing with the potential energy due to gravitation and springs, the sum of that. Okay, so potential energy from two sources. So the graph illustrates the potential energy only from the jump point to the turning point. All right, so we're going from a positive x all the way down through x equals 0 to a turning point. So a couple other key things here. Between x equals 9 and x equals 0, it's just free fall. So this is just a reduction in potential energy because of a reduction in height from the Earth. So that's a straight line till you get to 0. And then the spring potential energy kicks in. All right, at x equals 0, that's where free fall ends and the cord begins to stretch. At this point right here, right there, the slope of the curve is 0, which means force is 0. Remember, it's an equilibrium point. Okay, so that means the net force is 0. Doesn't mean they stop moving. It just means the net force is 0. And as they keep moving, then that's going to store more energy in the spring. Right? And the potential energy of the spring, the potential energy of the system starts increasing again as the spring gets stretched. Right? As it's stretched, it's storing energy. So the potential energy on this left curve here, okay, is mostly due to the spring storing energy. So let's divide this problem up into two parts. The first is going to be at x greater than 0. All right, that's the free fall portion. All right, here the cord does not behave like a spring. Right, so it doesn't contribute to potential energy. So the potential energy, so total potential energy, because that's what we're graphing, let's just do it for completeness sake, is going to be mgh plus the potential energy due to the spring, which is 1/2 k x squared, but that's going to be 0, right? Because the cord is not stretched yet. X is 0. So U is just mgh. So our potential energy is the 70 kilograms times 9.81 meters per second squared times the height, which is 9 meters. And that gives us a value of 6,180 joules. Okay, so we know, oops, coming back, there we go. We know this value right here now, up in this graph, is 6,180 joules. All right, that's the potential energy from the 0 point to the jump point, between the 0 point and the jump point, right, falling this distance. All right, so next, let's deal with x less than 0. It's a more complicated situation, because now we do have both terms. All right, so we're going to have the potential energy is mg x plus 1/2 k x squared. Okay, where x is the distance from x equals 0 to the turning point. Okay, so the potential energy then becomes mass 70 times 9.81 times x plus 1/2 times 150. This is newtons per meter square, newtons per meter, so its units are okay. I'm not going to put them in. X squared. Okay, so just to simplify this, this comes out to 687x plus, oh, this is supposed to be 150, plus 75x squared. All right, so to find the turning point, we know from x greater than 0, from that analysis, we know U equals 6180 joules. Okay, and 6180 joules, and at the turning point, kinetic energy equals 0, so total energy is just U. So that means 6180 must equal 687x plus 75x squared. And we know that our answer, x, must be less than 0 from our coordinate system. And when you solve this quadratic, you end up with an x equals minus 14.7 meters. All right. Okay, that's the tail of our bungee jumper. In the next video, I'm going to deal with finishing what we didn't finish in class on section 8.3 last Wednesday.